All right. Thank you, everyone online, and thank you here in the room. And welcome to Strait Science. Strait Science is an evening seminar series put on by University of Alaska Fairbanks Northwest Campus, right here, this room, as well as University of Alaska Fairbanks Alaska Sea Grant. And you're looking at the Bering Strait agent. University of Alaska Fairbanks Northwest Campus and Alaska Sea Grant, we are public servants of the Bering Strait region. We serve all peoples throughout the Bering Strait region, which is the homeland and waters of the Inupiat, St. Lawrence Island Yupik, and Central Yupik peoples. And with that, we will get started here in a minute. We've got, I think, Colleen Iversen. She is with Oak Ridge National Lab, and you'll be leading off. And she has a number of her colleagues here tonight, and they're going to be reporting on the NGEE project, which is the Next Generation Ecosystems project. And they've been actually here, and Bob Bolton is here. They've been here since 2016 in the region, and they have a larger project, and from here all the way to Utqiagvik. And what they've been doing here, they're going to talk about tonight, and imagine the data set they have since 2016. So we're really glad to see the whole group and meet Colleen in person and see Bob Iversen again. And with that, take it away. Colleen is the director of this whole project, and it's an enormous task, I'm sure. With that, come on and tell us all about it. Thank you so much for being here.
Yay! Hi, everyone online. I'm so glad you could join us today. And I wanted to mention, so I'm Colleen Iversen. I'm the director of the NGEE Arctic project. I took over from the previous director, Stan Wolschlager, when he retired in January of 2023, but he sends his best as well. And he has been texting Bob and I following along on this trip. So I don't know if you can see it, probably not since we turned the camera off, but I have 12 of my colleagues here with me to talk to you about the NGEE Arctic project. And of course, we have an acronym since we are funded by the Department of Energy. So Next Generation Ecosystem Experiments in the Arctic. We partner with multiple institutions. So in 2012, the Department of Energy came to Oak Ridge National Laboratory and asked us to do science in a way that spans institutions, in a way that spans disciplines. And so I have a little equation here on the title slide that is observations plus models helps us answer big questions across the Arctic. So let me say thank you to Gay for being such a wonderful host for us here at UAF Northwest and also the Alaska Sea Grant. And let me tell you about our partner institutions here on the title slide. So we have folks here from Oak Ridge National Laboratory, from Los Alamos National Laboratory, from Lawrence Berkeley National Laboratory, and from the University of Alaska in Fairbanks. So one of the things that we've been doing is telling folks how grateful we are to have been able to work on lands here on the Seward Peninsula since 2016. We just flew in from Utqiagvik, where we gave a talk there to let folks know what we've been able to find on the Barrow Environmental Observatory since 2012. And so we wanted to share with you some stories. I do a little embroidery, and I just wanted to mention, in addition to the scientific inspiration that we've had here, we've also had inspiration in spending time on your beautiful tundra. And so it's inspired some of my embroideries over the years as well. So I mentioned that we're supported by the Department of Energy's Office of Science, but the lands that we've worked on are lands stewarded by Native communities. And so UIC Science in Utqiagvik, and here we've worked on lands owned by Council, Mary's Igloo, Sitnasak, and Bering Straits Native corporations. And so we're very grateful to be able to have worked on their lands for this long. And we are also grateful to our advisory board, as well as folks here in Nome and Utqiagvik for all of the advice that they've given us over the years. And because we are a big project with between 100 and 150 people, depending on the year, we think a lot about open science and teamwork and inclusion and safety. So the NGEE Arctic team is big. It spans institutions and disciplines. So in addition to having For institutional partners, we have computer modelers, we have data scientists, we have boots on the ground folks who go out and make measurements. And so we've all had to learn over the years how to speak each other's language. So mathematical language for folks like me who are measurers, and then modelers coming to the field and learning about the importance of duct tape and tying up your boots before you head out on the tundra. So I wanted to mention, I've talked a little bit about the Department of Energy and national labs. And before I moved to Tennessee from Michigan to do my graduate work, I didn't know there was such a thing as national laboratories. And so other folks might not know either. And there are 17 national laboratories across the country, and we're representing 4 of those from Tennessee, New Mexico, and California. We used to have a partner at Brookhaven as well in New York on Long Island. And then, of course, it was so important for us to partner with folks at the University of Alaska Fairbanks as we first made our way to the Arctic of Alaska in 2012. So the overall goal of the NGEE Arctic project is really to make observations that help to improve models. I like to show this image from Victor Leshik in Arizona because it encompasses all of the parts of the Arctic that are rapidly changing in response to warming that is happening 4 times faster here than the rest of the world. And so some of the things we were thinking about in Utqiagvik on the North Slope, we're thinking about subsidence from ice melt and permafrost thaw. And further south here on the Seward Peninsula, we're thinking about shrubs marching across the tundra and trapping snow, increasingly frequent wildfires, sloughing of hill slopes. And so we could never think or measure the entirety of the Arctic. It's vast, and we couldn't possibly walk to everywhere we want to walk. And so we were putting together these observations like pieces of a puzzle into a virtual Earth. So the goal of our project is to build a virtual Arctic so that we can do experiments with it, so that we don't have to do experiments with the real world. And so when we started here, the computer models that we're using to make this virtual world didn't do a very good job of representing important processes like permafrost and ice. So in the first phase of NGEE Arctic, which started in 2012, really what we were doing was thinking about where the current generation of models that help us build this virtual world didn't do a good job, and focusing our observations on that. In the second phase, we had figured out all of these ways that we wanted to improve the model, but we couldn't add them all to the model. And so we had to think about what the priority additions to the model might be to make sure that we could correctly predict what's happening currently in the Arctic and also into the future. And then in this third phase that's ending in 4 days at the end of this fiscal year, we sort of tinkered with 6 parts of the model. So we wanted to improve the way the model represented snow and bacteria and plants and disturbances. And then all of those observations that we've made and the improvements we've made in the land system of the model fit like a bigger puzzle piece into an entire virtual Earth that has oceans and atmosphere. And so we can really predict what the climate of the future might be now that we do a better job of predicting what happens in the Arctic. Because as we all know, what happens in the Arctic doesn't stay in the Arctic, and it matters for the rest of the world. And so the fourth and final phase of the NGEE Arctic project, the Department of Energy has asked us to take what we've learned in Utqiagvik and in Nome on the road, take the model on the road. We've improved it based on observations across Arctic Alaska, but can we predict what is happening at other long-term sites across the Arctic in Canada and Sweden and Norway, publicly available data from Siberia, or do we need to keep working on our virtual Earth to better represent other systems outside of Alaska? So I mentioned that we were grateful to have been able to work on native lands here. And this is actually an image built from remotely sensed data of the watershed we worked on out on Council Road, nearby the historic Council Village there. And we were really happy to partner with other federal agencies. We partner with NASA because, as I mentioned, we could never walk far enough to make observations in all of the places that we want to. And so we use data from drones and aircraft and satellites to help extrapolate observations that we're able to make across the landscape. And we do that in partnership with NASA. And you can see also that the NGEE Arctic team of scientists, measurers, and modelers often are out on the tundra across all of the different seasons. So today we wanted to share a few stories with you about our scientific findings on the Seward Peninsula. We have over 250 data sets publicly available because we're funded by taxpayer dollars. And so we make our data publicly available, but not everyone can interpret the data that comes in from the observations we make. And so it's really important for us to be able to talk to the communities and sort of tell you a few stories about what we found. And we were able to talk to lots of students also in Utqiagvik, and that's important as well for the next generation of folks to understand how precious the permafrost is here. And so I mentioned that I brought with me 12 colleagues from across our institutions. And so several of those colleagues are going to tell you their own stories. And then I'm going to wrap it up at the end, and hopefully you'll have some hard questions for them at the end of the presentation. So I think Bailey is up first.
Hey. All right. Okay, so I'm Bailey Murphy from Oak Ridge National Lab, and Sigrid Dingle from Lawrence Berkeley National Lab, and I are going to talk a little bit about exchanges between the land surface and the atmosphere at Council, and how we measure them using a technique called eddy covariance. So the land surface and the atmosphere are constantly exchanging things, and this includes things like energy, water vapor, and gases like carbon dioxide and methane. And we call these exchanges between the atmosphere and the land surface fluxes. And so here we're going to mostly just focus on carbon dioxide and methane, because these are two really important greenhouse gases that contribute to climate change by trapping heat energy in the atmosphere and leading to changes in temperature that we experience on Earth. And so we measure these fluxes using a technique called eddy covariance. And so when I say eddy covariance, eddies refers to these kind of swirling blobs of air. So air moves kind of like how water moves. And when I say covariance, it means changing together. So we're measuring how the concentration of gases in these swirling blobs of air I'm not understanding that messaging. Okay, sorry. So we're measuring how changes in concentrations of gases in these swirling blobs of air is changing as the air moves. And these measurements are really high frequency. So we're measuring sometimes up to 20 times in a single second. And so we're interested in these measurements because we want to see if ecosystems like the tundra are overall net sinks or net sources of gases like carbon dioxide and methane. And so if an ecosystem is a net sink of carbon dioxide or methane, it means that the plants in the ecosystem are taking up more carbon than they're releasing to the atmosphere. And if an ecosystem is a net source, it means that the ecosystem is releasing more carbon to the atmosphere than it's taking up. And so we care about whether ecosystems are overall net sources or net sinks of carbon, and we care about whether that carbon is being exchanged in the form of carbon dioxide or methane, which has a much higher warming potential than CO2, because these exchanges of gases have really important consequences for things like the rate of warming that we experience. And so studying these exchanges in high latitude systems like the Arctic is really important because, as Colleen said, the Arctic is warming a lot faster than the rest of the world, so 2 to 4 times as fast. So as scientists, we want to figure out, why is it warming so much faster? And what does that mean? What are the global consequences of that warming? So I'll pass it off to Sigrid to talk about some of the instruments that we have on the eddy covariance flux tower.
Okay. Change a bit. Yeah, here we go. So welcome to council. And some of you that have driven to council, they might have seen our system on the left-hand side approaching Bear Creek. And so I'm showing here how the system was, how it looked. We unfortunately had to take it down last year. So to the measurements, we have been using wind sensors that give us 3 different types of wind speed. You can see in the image, for those people that can see the images. I can see it. And we have some, we also have gas analyzers that measure CO2, water vapor, and methane. In addition to these, we also measure air temperature and relative humidity, as well as incoming and reflective sunlight. And for our measurements, we also, to get correct fluxes, we also measure soil properties like soil heat flux, soil moisture, and soil temperature. And if you're wondering if Council is a unique site, well, it is kind of unique. We were, for the Syria Peninsula, we were the first people to do long-term measurements here as well. It's currently also the most western site in the US. When we look globally, no, sorry, I apologize. So once the system is running, obviously we don't measure in one single point. The system itself is measuring over a larger area, and thanks to the wind pattern, wind direction pattern in Council, we see over an area that is to the north that is rather dry, and an area towards the south that is permeated by channels, drainage channels, little ponds, bigger ponds, and wet areas. And in order to understand the fluxes properly, we also need a detailed or high resolution vegetation map that has also been created as part of this project. And if you ask again, my previous question, if it is unique, well, it is for us. And globally, well, not so much. There are currently over 900 sites that measure CO2 fluxes. Regarding methane, there are not 900 sites, because not all the sites measure methane, but we know that we can see on the world map, for those that can see the map, that the majority of sites are in the US. The US has currently over 600 sites, not all active, and Europe. But we also see that there are only a few sites in the high latitudes, Arctic and subarctic. And having said that, not all sites are long-term sites. There are many sites that only measure for short times, a few weeks, a few months only, which makes it very difficult to monitor changes over time. This obviously limits our understanding of the Arctic ecosystem dynamics, and also how these rather complex systems are reacting and changing, are reacting to a changing climate in the future. And the question is, why do only so few sites in the Arctic? Well, it is challenging to do these measurements. And you may ask yourself why? Well, the biggest challenge is accessibility and power. And we all know, even Council itself, it counts as a remote site, because many of us know that Council is not accessible all year round by car. You only have access to the site itself 4 or 5 months a year. And in terms of the second most important, second highest challenge, power. Well, in the high latitudes, if you have a solar panel that is totally covered in snow and ice, days are very short. There are days without any sunlight, especially up in the high Arctic. So using solar panels is not the best way forward. But at the same time as well, wind turbines can break, the blades can break, they can deblade by just disintegrating. But also instruments themselves, they can be covered in ice and snow, which again, they don't measure correctly. And in addition to that, we also have obviously animals. Animals are a very big problem at sites. Birds that land on these nice high spots on open tundra, they scratch instruments, they also deposit on them, which again leads to incorrect readings. We also have bigger animals that use them as nice scratching posts. They can break instruments, they can bend towers, they can even break towers and totally destroy them. We had sites in the upper Point Barrow that got destroyed every single year. But we also have small animals like foxes that do like cables. Pretty much every single year we travel to our sites with spare cables because they always get eaten. So, and of course, there are other issues like once we have finally data, even if we measure 10 times per second, 7 days a week, 52 weeks a year, even if we have no gaps in data, after all the data processing, filtering, quality control, if we have 50% of data remaining for an Arctic site, that is a lot. So that's also the end fluxes. The data coverage is very limited, even if you have a site that runs a year round. So, yes.
There's a question in the chat.
Oh, I
from
don't see
Rick
the screen at
Tillman.
all.
So, just
Oh.
if you, I don't think we need to repeat it to the audience because they can see it. And he asks
Oh.
for Sigrid, I think that's you.
Yes.
For any problems with llama?
Yes, actually, I have the llama in my bag as a unit. So for those that don't know the llama, I always carry a tiny little llama with me. It has its own Twitter account, and that became over time a bit unofficial mascot for the project.
We love it. Thanks, Sigrid.
Thank you. So yeah, I don't see the screen at all, so I'm very hard to see. So yeah,
No, don't worry about it. I'll let you know if there's questions.
okay, thank you, because it's obstructed in the front here.
Yeah.
So yeah, so I'm handing it back over to Bailey. Thank you.
Okay, so we're collecting all this data with the Flux Tower at Council, but what are we actually using it for? So one of the things that we're using this data for is to quantify tundra greenhouse gas fluxes. So we can answer questions like, is the Council tundra site overall a net sink or a net source for carbon dioxide and methane? We're also looking at using the data to understand environmental drivers of fluxes. So how different environmental conditions affect the exchanges between the land surface and the atmosphere. And hopefully we can use that understanding to try and estimate the future sink or source status of the tundra. So thinking about things like, will methane emissions over time increase and offset carbon uptake? So ultimately turning the tundra site into a net carbon source. Another thing we're using the data for is comparing against land surface models. So we can see how well our models are doing and where we might need to work on improving those models so that they can better match the reality of what's going on. And ultimately we can use those models to try and figure out kind of beyond the site scale, moving to this pan-Arctic broader picture, thinking about carbon budget calculations. And something that's pretty cool about this site in particular is it's not just the scientists that are talking to you today that care about the data from this tower. A lot of scientists are interested in what's going on at Council. The data has been downloaded over 2,000 times. So we've learned a lot over the course of 7 years from the data collected at the Council site. Some of the things that we've learned are that the tundra plants at Council overall absorb more CO2 than they're releasing. And we've observed that there are larger methane fluxes in wetter areas. So for those of you that can see online in this figure here, we're showing methane flux on the top and carbon dioxide flux on the bottom. And you can see that this green line that shows fluxes from wet tundra over time is pretty far away from this blue line that shows methane fluxes from dry tundra over time. Another thing that we've learned is that the tundra is really heterogeneous and it's rapidly changing. And so we're trying to capitalize on some of the data that we've collected from this tower and pull in this detailed vegetation map that we now have to try and continue learning about the relationships between vegetation and the land surface above and below and how they relate to some of these fluxes.
Okay, with that, we're going to change gears a little bit and talk a little bit more about the land instead of the atmosphere. My name is Shannon Dillard. I'm from Los Alamos National Lab in New Mexico, and along with Katrina Bennett, who is the institutional lead for the NGEE Arctic project at Los Alamos, we're going to tell you a story about snow and shrubs. Katrina and I, this is our second trip to Nome this summer, and we're really happy to be here. So thanks for welcoming us. So we know that shrubs are increasing across the tundra, and we also know that they grow quite quickly. A shrub can grow 3 feet in less than a decade, in about 8 years. And I'm sure you all have seen the changes in the tundra as the shrubs are growing into areas where they weren't before. We also know that climate change can accelerate shrubification. That's a word that we as scientists made up to describe this term. And this is happening in many different ways. Some examples of this are longer growing seasons, we know that the early spring is warmer and the early fall is warmer than it once was, which means that shrubs have a longer season on which to put on growth. Another climate change related scenario that's accelerating shrubification is that shrubs are moving into places that were once not hospitable for them. So maybe they were too wet, or maybe they were not wet enough. Maybe they were too cold, but those areas are changing. And so shrubs can move in. And another example, as Bailey talked about, there's more CO2 in the atmosphere. And because we know that plants are breathing CO2, they have more opportunity for photosynthesis. There's more CO2 that they can breathe in to put on green new leaves. We also know that the shrubs that are growing across the landscape can impact subsistence activities. And we'll talk about that a little bit later. So I'm showing a map here that for once is focused on the North Pole instead of on the equator. And so Alaska is here, but we can see this trend is across the Arctic, that the Arctic is getting greener. And really what we mean is it's getting shrubbier and more forested, as indicated by the green, except for this area in Siberia. And all of these dots or diamonds or squares are areas where observations or studies have taken place on tundra plants, including some right here on our very own Seward Peninsula. So to take us to the Seward Peninsula, these are some areas where we've done pretty extensive research. We've done research on all three of the roads on the Seward Peninsula, the Teller Road, the Cougar Road, and out to Council, as Bailey and Sigrid mentioned. Our site on the Teller Road is about mile marker 27. We call this the Teller Watershed. And our site off the Cougar Road is at mile marker 64 near Swan Lake. I'm showing these aerial images on the right-hand side, and you can see just how green these areas are in the peak growing season, with these really dark green areas, sorry, I lost my mouse here. Here on the Cougar Hill Slope, and here at Teller, these super green areas are the really shrubby areas. So some conclusions that we've learned from studying shrubs in these areas are that they're like Goldilocks. They like to grow where it's not too wet, but also where it's not too dry. What ends up happening, if you can picture a hill, is that they like to grow right in the middle of the hill slope, where the nutrients are just right and where it's not too wet and not too dry. And so these photos these images on the right side of the screen are showing, it's sort of like a heat map, where the dark red are the areas where there are many shrubs. This is really evident in this top picture here, where you see the middle of the hill slope here. And can you see my mouse? Yeah. The middle of the hill slope here are the areas that are really full of shrubs, indicated in red. Similar here at the same site. This is true for both alders and for willows, for large willow shrubs. And we're finding that at the sites at off both the Council Road and off the Cougar Road and the Teller Road. And I'm going to pass it over to Katrine.
Thanks, Shannon. Hi, everybody. So happy to be here back in Nome and joining you all for this Strait Science presentation today. So I'm just going to expand on what Shannon introduced and talk a little bit about sort of the snowpack and how shrubs and snow interact in interesting ways that we've learned over the years that we've been working out here at Cougar and Teller sites. So one thing that we've learned is that the winter soil temperatures are really warmest beneath the tall shrubs. And this is largely because of how the shrubs are capturing and entraining the snowpack. So in this figure on the right-hand side, which is sort of a pictograph, you can see that the snowpack is deeper underneath those shrubs, and the snow actually acts like a blanket over the snow acts as a blanket over the soil, and this actually warms the soil and leads to deeper active layers and less permafrost over time. And in areas where we don't have deeper snowpacks, we see that the soil is actually less warm or cooler. And that is changing, of course, as we're seeing an increase in the shrubs across these systems, like Shannon talked about. So the other thing that we have learned from our studies that we've been focusing on across the Seward Peninsula is that while, shrubs are really, really important in terms of capturing and entraining that snowpack, topography is also really important in terms of capturing and drifting snow. So wind blows snow into the topographic hollows and across the hills, or it's captured, say, for instance, in the stream bed of the Teller watershed. And so we see sort of variation across the watersheds in terms of snow depth. And that drifting is really, really important, as I said earlier, because those deeper packs tend to insulate the soil, and then that can increase the thawing of the permafrost underneath. So over the years, and we have been working out here since 2016, as we talked about earlier, we made a lot of snow observations over these years. So we actually went out for 6 years, 2016 through 2019. And we took a little break for the pandemic, and we came back in 2022 and 2023 to finish the surveys off. And so on the left-hand side of this slide, I'm showing you the Teller watershed just as an example. Across both Teller and Utqiagvik, we made over 40,000 measurements of snow depth and also what we call SWE, or snow water equivalent. And that is just the amount of water that's held in the snowpack. And that's really important for us to understand, because that water that's held in the snowpack is released in the spring when the snow melts, and that infiltrates into the soil and leads to wetter soils, and also thawing permafrost eventually. And on the right-hand side of the slide, I just have a couple of images of our team that were out there. Of course, as Colleen talked about earlier, this is a really great large project where we have had a lot of collaboration in terms of all of the different entities, all of the different labs that have worked on the project. And of course, for this work in particular, we've had a lot of great support from the University of Alaska Fairbanks. And so we had a lot of fun out there measuring the snowpack in different ways. I'm showing Lauren here probing the depth of the snowpack. Ryan is digging a hole, and I think he's being helped out by Stan in the back potentially. And then Claire is walking away from the helicopter that we use to access these sites in the wintertime. So all of this data that we collected is going into our models that are predicting snowpack. And one of the big goals of this project was to improve the Earth system model. As Colleen mentioned in the very sort of introduction of our talk, the model originally didn't represent these Arctic systems that well. And so we've been trying to use a series of finer scale models to learn about how the snowpack was being represented. We are comparing it with remote sensing data. As I'm showing in the right-hand side of the slide, we have our LiDAR data collected in 2022 against our model on the right-hand side for both Teller on the top and Utqiagvik on the bottom. And so we were able to see how well we were doing and then use that to improve our predictions in our Earth system model. And predicting snowpack is really important for many things in terms of predicting the future climate change impacts that we're going to be seeing here on the Seward Peninsula of Alaska. But of course, that's also really important for humans who are interested in collecting berries across the Seward Peninsula and are interested, or we're trying to understand how those berries may change in time with different changes in terms of soil moisture regimes. It's also really important in terms of wildlife habitat and of course subsistence hunting as well, since wildlife is also very affected by these changes in the land surface that we're able to observe. So I will pass it back to Colleen at this point. Thank you so much.
Okay. Short. There you go. So you've heard just a few of the many stories that we have as part of the project that has been ongoing for 12 years now. And I hope it helps you understand that it's important that we have scientists on the project that can measure each of the aspects of the rapidly changing Arctic. And I like to think of these stories as sort of two pieces of a big puzzle that we're putting together. And we happen to be building a puzzle in virtual space. We're building a virtual Earth. But we need to understand each and every part of the changing Arctic in order to be able to say we're confident in understanding what's happening now, but also to have some confidence in future predictions, right? We want to know what the future might hold in terms of climate change for the Arctic, but also because the Arctic is so important as a part of the climate implications for the rest of the world. And so what we're doing starting on October 1st is the fourth phase of the project. And so we're asking whether this understanding in virtual space and also in the real world that we've built based on the observations that we've made on the Seward Peninsula allows us to predict what's happening across the rest of the Arctic. So we're taking this model on the road and comparing it to long-term data from these sites to see if our improved models with snow and permafrost and tall shrubs can better predict what's happening than the models could previously at these sites. And so we have a couple of stories that we wanted to share online with you as well. And so you can check out these links here because I think sometimes it's important to see what's happening in the Arctic. And so folks like Julian have helped us build story maps to show, you heard the stories today from each of the sites that we've worked on, the Council Native Corporation land off of Council Road, Mary's Igloo land off of Cougarok Road, and Sitnosuk land off of Teller Road. And so we wanted to show in pictures and in stories what we've been able to find. And so you can check out these links for more information there. And also sort of hear voices on both of those links of the scientists telling their own story. And you can hear podcasts as well. And really why we're here today is to say thank you. Thank you for allowing us to work here on the Seward Peninsula on your lands. And we are always happy to tell you more stories. And so let us know if you would like to speak to any of the 100 scientists on the project. They can talk your ear off about the science that they have been doing. So I hope you will ask us some hard questions, and we thank you very much for tuning in tonight.
Let's see, I'll come, well, you stay up here. No, you stay up here. If they're gonna be hard questions, you gotta be up here for that. Get it right in there. Right in there. There you go. There you go. All right, so, don't wanna leave this behind. At this time in straight science, this is when the audience usually, because it's never easy to be a public speaker, this is when we ask the audience to show a little love for Colleen and her team in the chat box. And if you have any questions or you're thinking on your questions, when you're done with the chat box, then ask away. You're already getting some hearts and there's some kind of I'm not that good on Zoom, but I see people are, and they've got hearts and whistles and things like that. All good. So I'll start off since, let's see if we've got anything at the moment. Thanks, Rick. I have a question. So here at Northwest Campus, I'm more marine, but we have, algae, but we have the Korean Oceanographic Polar Research Institute, known as COPRI, and they're a feature here every summer. And they seem to work on the Council Road too. Are you guys like combining and sharing your data? Things like that?
Yep. We collaborate with COPRI, and we've done some remote sensing observations in collaboration with them. And we have a project-wide seminar series, and COPRI is on the schedule for October or so to tell us about what they find. And so we're very happy to get together with other folks measuring in similar places.
Yeah, awesome. So my big question is, will you come back after you double check with all the, looks like the different countries, that last map with all the,
Getting 5 of the 8. Yeah.
yeah, I probably can't go over to Russia.
Publicly available data.
publicly available data, but you're gonna travel or you're just gonna sit and,
We have
Virtual.
collaborators working with us, so they're gonna collaborate with us and provide us data, and we're gonna work on the models together.
awesome.
Mhm.
So, all right. And I had a question for, I know that we have UIC, which is the, from, what is the?
Utqiagvik Corporation.
Yep, Inupiaq Corporation, and they do a lot of the science, logistics and help for researchers when you're in the North Slope Borough. And down in the Bering Strait region, we don't have such a great resource as they are. And I'm wondering, do you get help locally for your, when Sigrid, sorry, was talking about her equipment and how the animals are chewing the cable and there's snow on the thing.
Yeah.
Is that something that people here were able to help you with, or?
In fact, during the pandemic, I think we subcontracted with Kenny Hughes to help do some tinkering on
Okay.
Sigrid's instruments.
All right, wonderful.
Yeah, and we've been able to rent apartments from the Martinson family over all these years as well. And so we've got lots of folks who've supported us while we've been here.
Awesome. That's wonderful. So I'm glad to hear that too. That's wonderful. So Rick Toman has a question in the chat for the snow experts.
Which
So get ready. Oh, you don't, well, okay. All right. For the snow experts.
got the camera.
Fall on us.
Oh,
Get right in there. Sorry, it's gonna
Okay.
fall over.
Hello.
So the question is, there is effectively no near real-time snow depth. SWE, Rick, you're gonna have to,
Snow water equivalent.
snow
Yeah.
water equivalent.
Yes.
Observations on the Seward Peninsula. You really are an expert. Do you have any suggestions for quote, best practices as we try to get snow observations restarted?
Hmm.
I want to read it again.
Yeah, I guess that's a great chance for me to talk about one thing that we have been doing that I think is really novel. We've worked very closely, of course, on this project with Berkeley National Laboratory, and they put in a network of what they called distributed temperature profilers. And then we coupled that as well with iButtons, so tiny temperature sensors that we were able to spread out across the entire study sites. And so with those two measurements together, we've been able to actually model using some simple machine learning techniques, snow depth from that ground surface temperature alone. And it's really kind of exciting, I guess, surprising discovery. We're able to develop those models, again, based on that fantastic Berkeley data for our study site here, but then we were able to test them across almost the whole Arctic and even as far south as Colorado and New Mexico. And they did okay. They did less well in the lower 48 sites, but they did well in the other sites, which was really an exciting discovery for us. So I think this is kind of opening a door with sort of large data collections coupled with machine learning to answer some really challenging science questions that I think the community is facing in terms of snow water equivalent estimates and things like that. So.
All right, which actually makes me think of a snow question, because we're all about snow kind of up
Yes,
here.
snow is.
And you had from 2016 to 2019, and then you
Right.
stopped for the pandemic. So
Right.
right in there, that 2017, 2018, 2019, those were
Right.
very warm years
Okay.
for our sea ice anyway. And Rick
Mhm.
Toman, I'm glad you're online, but I think it was pretty warm winters overall.
Yeah. Okay.
And then you took a pause,
Mhm.
and then you've come back.
Right.
And we have this year, which
Mhm.
seems really cooler for
Okay.
us here.
Right.
It may be warmer all over, but it's very cool for us here overall
Yeah.
with our water temperature, our ocean temperature, and then our snow, and then the ice that we actually have ice, I believe, right now in the Strait, right?
Okay.
It's coming down. It's
Yeah.
already around Cape Dejnev. So,
Right.
so we are a little bit colder. Is that when you capture those kind of things, are you able to,
Like represent them.
yeah,
Yeah.
how do you, those are some extremes, I think.
Yeah. No,
In
it's
the wet, we just,
right. Really.
also were
rainy.
extremely rainy, and moisture rich this year.
yeah,
So
yeah.
we broke the over 100-year record,
Wow.
right, for moisture coming down in July and August. So everything, it's even affected the oceanography, right? So the salinity in the strait has changed because all our rivers, everybody is dumping water, was dumping
yeah.
water at horrific rate
Yes.
for a
yeah.
long period of time, for like 2 months. So how are you
Yeah.
able to sort of work all those? It just seems like it's swinging
Right.
really up and
Yes.
down.
Yeah. So we
Extreme.
2017 was a low year, 2018, 19, and 2022, I think were higher snow years. And so with, I believe 2019 slightly ahead of 2018, but there was differences in densities due to some rain on snow events that happened. So I think actually the exciting thing about this project was that we did capture that range of variability because we operated for so long. Like we were able to get those long-term measurements, which means, you know, if you have a project and you only go out 1 year or 2 years, you might not see that range of variability. So our models have enough data, enough observations to better capture a widely variable system, which I think is really key in order to develop a robust model to be able to really test it. So yeah, I think that was actually very helpful for us. And again, it is really about these long-term observations, long-term projects that are so important to really truly understand the science and represent it in models. Yeah, absolutely.
Bob Bolton coming up.
Trouble's coming.
No, it's good.
Yeah, so Bob Bolton here. And so going back to those really warm or like those really warm years that you were talking about.
Yeah.
We actually measured in this region we had really warm summers that were followed by really high snowfalls, and the snowfalls were early in the year. And so that trapped all that summer heat. And we had 2 years in a row, and then we had really warm winters.
On land, it trapped the summer heat
Under the snow.
Tundra, yeah,
So that
okay.
snow was a blanket, an insulating blanket. And then we had really warm winters on top of that. And then we had that cycle 2 years in a row. And the net result of that was we had 2 years in a row where the ground didn't completely freeze where we normally had it froze. So we didn't go through phase change with the soils. Usually we dip quite low below freezing, but we didn't go through that phase change, and so the active layer didn't completely freeze. And so then there were some other issues like up in the Red Dog area where they started getting more sediment loads, similar conditions. So the permafrost started falling apart a little bit during those times, and so it was kind of a cool.
Oh, so the permafrost didn't get a break?
No,
you're saying?
Yeah, so it wasn't able to regenerate itself, sort of.
Okay.
And so it was, and so if it doesn't freeze, then when you add more heat, then that heat doesn't have to go back and melt the ice or thaw the ground or any of those things.
Yeah, you should have seen what was going on with the sea ice in 2017, 18, and 19.
Yeah.
It was pretty impressively scary, actually, or just something to witness, to behold, actually.
Yeah, it was kind of a cool and scary thing at the same time.
Yeah.
Both things going on.
Yeah. So, I have a question for the willow experts. Watch yourself on this cord. And that is, what does it mean for us when you say we're getting more willows? We see that, right? Everybody sees there's this creep of the trees and the shrubs, any chance they can get. Will those seem to catch our snow, as you mentioned? So what's the impact that we should be thinking about as it looks like willow's the winner? I don't know if there's other plants that you are adding in your shrubification, but what should we expect in like moving forward, like the next 15 years or so?
Yeah, good question. So I'll start by saying on the Strait Peninsula, there are two main large shrubs. There's willows and there are alders. Out on the Teller Road, there are only willows, but alders are out on the Cougarock Road. And so as more shrubs grow and spread and catch snow, we know that the permafrost underneath those shrubs is going to get warmer, and it already has become warmer underneath those areas. I think Katrina may have mentioned that we know underneath the shrubs are the warmest areas, and we know that from several different types of measurements. And so what we might be seeing as shrubs are following like water tracks or they're in the middle of the hill slope, like the figures I showed, is that the permafrost loss might be accelerated in those areas. And so the areas that do still have soil ice will be losing ice faster underneath shrubs
Because
than,
what Bob Bolton was.
right,
Okay.
because they trap the snow or entrain the snow, like Katrina was saying, create a big blanket. And then also as that water melts, it's inputting all of that heat energy from water into the ground where ice may be.
Do you guys look at the ecology also? Like, will that make it better for the Arctic hare? Will that make it better for snowshoe hares? Will that make it better for ptarmigan? You know, that auger in and use those.
Yeah. Yeah,
Is that-
so there's no wildlife experts on our project, but as environmental scientists, as we go out and observe, we see wildlife out there all the
Yeah.
time, particularly muskox. And especially in the willow shrubs, we find their little sheds,
Kiviat.
okay, all throughout the willow shrubs. And so it's definitely habitat for them. Yeah.
Yeah.
And I'm sure a whole bunch of other things as well. We've seen Arctic fox race out of there. What else have you all seen? I'm sure others.
Well, I just mean with that snow load. So ptarmigan
Oh, with
and
the snow load.
ptarmigan and things like that will burrow in the snow to get out of extreme situations with our winter
Yeah.
weather.
So I'm sure that is winter habitat for
Okay.
them. Yeah.
All right.
I'm not a wildlife expert.
No, I'm sorry. I
but
didn't know. That's why I guess
I would be willing to bet that's winter habitat.
Yeah.
For them.
All
Yeah.
right.
Okay.
Well, good.
Can I add something
Yeah.
about that too? So, yeah.
I
So
see you, Dean.
one
And
second.
Peter.
Yeah. So our collaborators at NASA do make some wildlife measurements with their snow measurements. We've been trying to convince the modelers to put animals in the model, but we haven't had any luck so far. We actually wanted to start with beavers because they're such an important engineer of ecosystems in terms of hydrology and that sort of thing. But our collaborators at NASA are finding that depending on the year, the snow depth can impact the interactions between predators and prey. And so, caribou and wolves, wolves with big paddle feet and caribou with the sort of stilettos is the way that they talk about it. And so each sort of predator and prey has a different competitive advantage depending on how deep the snow is. And Katrina mentioned that rain on snow is happening more frequently as well and changing the density and changing the ability of different animals of different weights to sort of walk on the snow. And so that's something that our collaborators are looking at as well.
Awesome. There is a question in the chat. From Peter Bovang. Thanks for the informative presentation. Question. One figure showed a large number of flux towers, the vast majority on continental land masses. How are marine fluxes incorporated into the model? How are marine fluxes incorporated into the model?
Right, staring at me. Yeah. So the model that we work with is called the Energy Exascale Earth System Model. And so it is a model of the entire Earth, but groups break up depending on what sorts of things they study. And so there are teams that study the atmosphere in great detail. And there are teams that study the ocean in great detail. And our team studies the land in great detail. And so what we're doing is passing off information on the land surface. There's lots of folks who study marine fluxes, a lot of times from ships, but also from buoys, and also from machine learning, as Katrina mentioned. And so I'm going to leave it there because I don't study oceans. But they are incorporated into the ocean component of the model. But as I mentioned, it's sort of an interdisciplinary or collaborative effort to understand what's happening across the entire Earth. And what the model was lacking actually was the connection between the land surface and the ocean. It's just been added this last year. And so we are building bridges in virtual space there as well.
All right, thank you. Dean Stockwell, you had your hand up. Do you have a question for Colleen and her group?
Yes, I did. So you mentioned an increase in shrub coverage, and you focused primarily on alders and willows. Are you seeing any new shrub species in the area? Is there an increase in the smaller plant species?
Hi, Dean. Thanks for your question. So this is happening in parts of Alaska. We kind of call it like the northern creep, where plants that were doing better further south are coming north and north and north because it's not cold enough further south. We don't know of any new plants on the Seward Peninsula, or I don't know of any new plants on the Seward Peninsula. And as of right now, what we know about the competitive advantage of plants is that plants that are already here are out competing plants that are moving in. And so they're still the more suited to this habitat right now in 2024. In 100 years, that might be a different answer, but plants move pretty slowly overall. And so not yet, not right now.
Okay, understood.
Hopefully no
So,
ever.
so the loss of permafrost has co-occurred with increases of blue-green algae in a lot of the region to the east of you. And those types of increases in, I'm a phytoplankton person, so those types of increases in the phytoplankton are yielding increases in O2 and changes in CO2 fluxes. Are you seeing any types of things like that in riverine bases that you can focus or isolate? The loss of permafrost is also putting a lot of nutrients into the watershed.
Yeah. Yeah, so I could talk a little bit about nutrient loading, but in terms of algae in rivers, I'm not sure. Katrina, do you know anything about that? Yeah, unfortunately, we don't have a river person with us up here right now. But I do know that because of the loss of permafrost, there is nutrient loading into the nearby waterways as well as sediment loading. Yeah, so whether or not in these systems that creates the habitat for algal blooms is it hasn't been the scope of this project, but that information might be out there.
But those losses of permafrost are also giving you an increased methane signal. Are you picking up any of those? You're releasing that from the soil that's been locked in there by the permafrost. You're running away.
Hi, I was running up. Hi.
Hi.
So that is something that so Sigrid's picking that up with her eddy covariance tower, but what she's found and why it's so important to understand SWE or soil water equivalent is that, you know, methane only comes from areas that are anoxic or lacking oxygen in the soil. And so it's the wet areas, the areas that are becoming increasingly flooded. But sometimes the areas become drier as well, right? When you lose that permafrost, sometimes you have subsidence and you are drier, sometimes you have subsidence and you're wetter. And so methane fluxes really follow what the water is doing as well.
Thanks. Yep.
All right, there's another question in the chat, and that is by Rick Toman for the snow experts again. So gear up. All right, based on the Teller and Kugarok sites, can you give a ballpark estimate of typical snow depth variability across a typical transect? There we go.
Okay. Yeah,
You're on.
taking my memory here. No, I do want to say that the maximum snow depth that we measured and that our models sort of able to predict to, I think was 2.7 meters. And those, you know, likely the snow is deeper than that, you know, in the stream bed, for example, but we couldn't get to the stream bed. You know, it was difficult to measure, and we were limited as well by our measurements tools. So we had for very, very deep snowpacks, for example, we used avalanche probes, but they had a limitation on their depth. But yeah, I think I want to say between 70 and 90 centimeters was about on average what we saw across a typical transect in Teller, for example. And so, you know, that varied between, you know, where we were, you know, on the east side of Teller, for example, the snow was very shallow. And then we saw a lot of variability again around the shrubs, which we already talked about, also around the permafrost risers and treads. And in the stream bed, we know that that holds a lot of the snowpack. And actually in our modeling, we learned that topography, shrubs, and the sort of smaller features like the stream bed and the, so elevation, shrubs, and the smaller features like the stream bed and the top and the permafrost risers and treads were the major control on that snow distribution variability that we saw across the basin.
Can I ask a follow-up?
Go ahead.
Sure.
Yeah, so for years I've been kind of using some of the work that was done over the years in the Prudhoe Bay area, so over a 200-meter transect, snow depth would vary by 50 to 100% in what looks to the naked eye looks like a pretty homogeneous environment. Would you want to give a percent variability over 100, 200 meters as something typical that you've observed on the much wetter, much snowier Seward Peninsula environment compared to Prudhoe Bay land?
Yeah, we could share all the data with you. It's available publicly. So we have all of our data is actually pointed out on this slide. I think that it's on ES Dive already. So actually you could, if you wanted, we could look at those percentages together if you're interested. So yeah, I don't think I could pull a number out of my head right now, but I do want to say that was something specifically that we looked at, and that snow depth varies quite a bit across these systems that we look at. And that was what we were trying to improve in the model ultimately, was we knew that variability was controlled by that topography, those shrubs, and that was just not represented in the model. And that is one of the big contributions that we have made to improve this model.
Oh, great. Thank you.
Yeah, thanks.
All right. Well, we are rolled into 7:30. If there's no more questions in the chat, Peter Bovang said, thank you, by the way, for answering his question, whoever answered that one. And we will let these nice people go. So I don't see any other questions, but we will look forward to their return when they talk to the other people across the Arctic and see how the model has done, right? That's what we're all in for. And I do see, Rodney, I see you online. Is there any questions you have out on the island about what they're talking about with shrubification and permafrost loss? Any thoughts on that? You don't have to answer if you don't want. All right. So for the next Strait Science will be October 9th. And we are going to have the United States Special Operations Command, and they're going to tell us what happened with Operation Polar Dagger, which was a Bering Strait event that happened in July for most of the month. Actually, I think into August. So we're going to hear from them who they are, what happened here, and what are their plans as we move forward into the future. So that'll be a very interesting one for the Bering Strait region specifically. And we're thankful they are going to make themselves available. So with that, thank you all for coming and have a good night. We'll see you next time, October 9.